Hello there, and thank you for tuning in to follow my presentation titled Improving Traffic Intersection Safety with a Smart Roadside Unit. My name is Risto Ojala. I worked for 3 years as a research assistant in the Aalto Mechatronics Research Group. I've just finalized my master's thesis, and now I'm looking forward to moving into my doctoral studies. This presentation is designed to give a nice overview of all the research I've conducted so far, so let's jump right into it. Now, why focus on traffic intersections? Well, statistically speaking, traffic intersections are really hazardous areas in the road networks, as actually 20% of all traffic fatalities occur in intersections and junctions in the EU and US. This can be quite naturally understood, considering traffic intersections are these special areas in the road networks where road users are required to cross each other's paths. So in order for a road user to get to where they want to go, they actually have to kind of get in front of someone to get there. Now, this is of course very hazardous, and operating a vehicle in these areas naturally requires a lot of situational awareness and knowledge of the other road users from a driver. This can be hazardous, as a driver is of course prone to human error. So what I've been trying to do in my research is develop technologies that could help the driver operate the vehicle in these areas. And now I believe connected vehicle technology offers some great tools for achieving these goals. As with connected vehicle technology, we can actually feed information to the driver that the driver is not capable of acquiring from their point of view. Now, why is this important? Well, especially in urban intersections, the problem is oftentimes that the driver can't actually see the other road users approaching an intersection. This is because their visibility is quite limited by obstacles such as buildings, fences, flora, and other different obstacles that are blocking their line of sight, preventing them from seeing other road users approaching an intersection. And this of course poses a threat, as the driver's situational awareness is limited, as they do not know of all the road users approaching the intersection and their positions. And now what I believe would be a solution for this is actually utilizing all the cameras already installed in the road infrastructure, such as traffic cameras and surveillance cameras, equipping these cameras with machine vision algorithms that can be utilized to detect and localize all road users approaching an intersection area. The information acquired with these machine vision algorithms could then be sent over the internet to approaching connected vehicles. This way, the connected vehicle could effectively warn the driver if there is an apparent collision ahead. So basically this would mean that when a driver is approaching the intersection, their car could tell them, hey, there's a cyclist coming from your right, you are on collision course and you may have a collision in 5 seconds, you should probably slow down. And now this technology would not basically be limited to a driver. It could still be applied with autonomous vehicles, as the information could also be used in the decision making of an autonomous vehicle in intersection areas. Okay. I've actually been researching this technology right here at the Otaniemi campus of Aalto University. On the left here, you can see our research vehicle that has been equipped with an additional screen that allows the research vehicle to show the driver additional information when at our research intersection. On the top right here, you can see a camera that we have installed at the research intersection, and on the bottom right you get a better view of the research intersection, the position of the camera here indicated with the red circle. And the installed camera is capable of seeing all the road users approaching from the road marked with the red arrow, and the information of these road users can then be sent to the research vehicle when it's approaching from the direction of the blue arrow. Okay, so what have I actually been researching in this research environment then? Well, detection, so the ability to actually detect the road users from the camera view is of course a core mechanic in order to have this system functional. And I've developed an algorithm for this called Modecla, short for motion detection and classification, that is capable of quite accurately detecting road users from video feed. The algorithm is quite intuitive to explain, so I'll go through the images here, going through the processing steps of the algorithm step by step. So on the upper left corner here, we have just a normal frame from a video feed, and then in step A, what we are doing is we are actually performing motion detection on this frame. To explain this in a simplified manner is basically saying that we are looking at the current frame and the previous frame, and we are looking at the pixels that have changed. So if a pixel has changed value, then we can assume that there is motion in that part of the image. But now the result from the motion detection is quite noisy. You can see a lot of pixels, just single pixels detected as motion, and other type of noise. So in step B, we are actually performing some basic image filtering techniques to get a nicer view of the moving objects. And in step C, we are fitting these bounding boxes to these detected areas of motion. And in step D, we are actually using these bounding box coordinates to capture the relevant areas from the original image. Now in step E, we are actually applying a small convolutional neural network to classify these parts of the image. So we are able to actually know what's inside those boxes. You can see that there are the people, the pedestrians have been given a title person, and the car has been given a title car, and the box that doesn't actually contain any specific road user has been just titled miscellaneous MISC. Okay, so this is the algorithm that I've developed, and to give you an idea of how well it works, I'm going to show you a comparison to another detector that can be used for detecting road users from a camera view. This other algorithm is called YOLO V3, and it's a very big convolutional neural network, end-to-end convolutional neural network that takes an image as an input and then uses deep learning to detect all the road users present in the image. And here you can see a video of the two algorithms running side by side, and both algorithms are working quite well finding the road users here. YOLO V3 is making the mistake of thinking that those piles of snow are cars. That's not common behavior for it. It just happened with this data I had available right now. And well, now we can actually see one shortcoming of Modecla. So when the cars are passing each other here momentarily here, you can see that Modecla actually puts a single box for the cars. You can see it again here. Puts a single box for these multiple overlapping cars. Now this basically due to the motion detection step, Modecla has trouble detecting road users that appear on top of each other in the image. This is something that will require future work to get the detection working properly. But overall, the algorithms are both working quite fine. They are finding the road users present here. And for a bit more scientific comparison, here is a table showing the accuracies of Modecla and some other detection algorithms, and evaluating how well they are able to detect people and cars in the data that I've used in my tests. And now this accuracy is given as an average precision, which is quite difficult to explain, so I won't go into too much detail here. So let's just say that the bigger the number, the better the algorithm. And now looking at this table step by step, here in the first column, we can see the accuracy of the different detectors in just detecting the pedestrians there. And we can see that Modecla is performing quite well. Second best here, surpassed by this YOLO V3 that was shown to you previously, still beating all the other detectors compared against here, and quite close to the result of YOLO V3. Now, looking at cars, we can see that Modecla performed quite well again. Not as well compared to the other detectors as with the pedestrians, as we can see that it was the third best, outperformed by YOLO V3 and M2 DET. But still a good result. And then this here is just a mean average precision, so basically taking a mean of the previous values, and this allows us to have a kind of a final value to compare the detectors, and we can see that Modecla was ranked second best in the tests that I performed. But okay, why am I developing an algorithm, going through all the trouble if it's just the second best? Why not just use YOLO V3 since it is more accurate? Well, the reason is computational power. So basically, YOLO V3, as I said, it is a huge, deep neural network, so it requires a lot of computational power to run it in real time. So if you want to run YOLO V3 in real time at 30 frames per second, you basically need a big, powerful computer that pretty much costs you 1,000 to 2,000 euros. And this is of course too much if we want to actually see this technology out there on the road. We cannot afford to buy computational power of several thousands for each camera we want to equip with this technology. So Modecla is actually capable of running in real time with a small single board computer that only costs 100 euros, giving us a lot more efficient detection and actually making the solution scalable. The price is a lot lower and the algorithm is a lot more efficient, so that the system could actually be installed out there on the road. But okay, I've now talked about detection, and this was all about finding where the road users are on the screen. But if you want to go a bit further than that, if you want to actually know the positions of the road users in the real world, this is called localization, and we are actually able to find the positions in the real world as well with just a single camera. Oftentimes stereo vision is required to find depth information in images, but if we make certain assumptions, utilize the geometry presented here, we can use just a single camera to find the coordinates of the road users. So here we can see that we have the x coordinate and we have the y coordinate. And these coordinates can be calculated using this geometry, assuming that all the other parameters in the geometry are known here. I won't go into details of the mathematics, but following basic geometry, x and y can be derived from here. But okay, so then the problem becomes, how can we know all the other parameters for the camera? And well, for this, we have to perform camera calibration. And well, I've been researching the most efficient way to carry out this camera calibration, and I found I've developed an approach, a GPS-based approach for calibrating this camera. So in order to acquire all those other parameters for the camera, the only thing necessary is actually to just have a person visible in the camera view, capturing their GPS coordinates in multiple different points in the image. Then using these GPS coordinates as well as the pixel coordinates of the person in the image, we can optimize the parameters of the camera, kind of matching the GPS coordinates to the image points. And here is a kind of illustration of what it looks like. So we have a person, me, carrying out the calibration here in the image, and I have a GPS receiver with me, so I'm able to also get my coordinates in the real world. And now, once the camera is calibrated, what we are able to do with it is basically presented here. So we can see that we have an image here with a lot of road users in it, multiple people, multiple cars, and what we are actually able to acquire with the calibrated camera is this map presented here on the bottom right. So we can see that this graph the y-axis is north and the x-axis is east, so this is a kind of a world map, and we are able to actually get those detections of the road users and place them on the map. Now in this world frame, this drawing of the camera presents the orientation that the camera is actually in the world frame. And we can see that all the road users have been positioned quite nicely. We can see the two pedestrians next to each other. We can see one of the cars that is quite far back there, and we see the car that is quite close to the camera, and so on. But again, to look at this a bit more scientifically, let's look at some actual accuracy measurements. And these histograms are some exact measurements that I've carried out. On the left here we have training error, and this is basically the result of performing multiple calibrations with the camera using randomly selected data and looking what the localization error is like with the same points used for calibration. And we can see that there is still quite some error there. The calibration is not perfect. We have error that is somewhere between 4 to 5 meters on average, and this is already quite high. And then on the right here we have the testing error, and this error is the localization error with data points that have not been used in the calibration process. So these give a more realistic view of the actual accuracy of the system. And we can see that here the error is somewhere between 5 to 10 meters. So there is a clear error. We are not able to get exact positions with this system yet. So the reason why there is so much error in these measurements is basically because the camera has now been calibrated with a consumer grade GPS receiver. And now consumer grade GPS contains a fair bit of error. It is quite regular, quite expected that you can have errors higher than 5 meters in the measurements. So this means that the calibration has not been perfect. Has not been perfect. Instead, it's this kind of these tests have been a kind of proof of concept, an initial calibration for the camera. Now, more testing is required to prove that this localization is can be done better. So, what I'm working on next is actually using a high precision RTK GPS device, which is capable of getting accuracy in the range of tens of centimeters. And in my future work, I'll be calibrating the camera with this accurate RTK GPS, and then looking how accurate we can make this camera-based localization. This covered all the topics. I've now covered all the topics I wanted to talk about. So as a conclusion, my research work is focused on machine vision roadside units for traffic intersection areas. And the overall idea is to use traffic and surveillance cameras, apply machine vision, acquire positions of road users, and send this information to connected vehicles approaching the intersection. And so effectively, we are able to provide the driver information that they are not able to see from their own point of view. And now, in order to actually, if we someday want to actually have this system out there on the roads, the detection and localization have to be accurate, fast, and cheap. And this is what I spent my time researching and developing. Now, thank you for your time. If there are any questions, please feel free to contact me at my email, and I'll be happy to answer them. Thank you very much.